Alright, let's talk about uniform circular motion. Now, when we talk about uniform circular motion, what we're talking about is something that is moving in a circle at a constant speed. Now, the reason I'm going to be saying speed and not velocity here is because by definition, right, velocity is speed and direction. So if something is moving in a circle, it is accelerating, right? Because at any given point, it is changing direction. So you want to be kind of careful with the language there, especially in some of these written answers when it comes to anything moving in uniform circular motion. You want to make sure that you're talking about speed being constant and not velocity, because velocity does change because there's a directional change. Now, this acceleration that the object undergoes during circular motion is a very specific acceleration, and it's what we call the centripetal acceleration. And the centripetal acceleration can be found by taking the speed squared over the radius of the circular path. Now, centripetal comes from the Latin for center seeking. So if you look at the notes, and I would advise looking at the notes simultaneously as you go through this video, because there are a lot of good images there. You'll notice that the acceleration is always directed straight towards the center of that circular path. Right? Again, centripetal, Latin for center seeking. That acceleration is a center seeking acceleration. Now notice also that the instantaneous velocity, the speed at any given point on that circular path, is going to be tangential to the centripetal acceleration, meaning it's going to have a 90-degree angle to that centripetal acceleration. So if we take a look at conceptual example 6.1, rounding a corner, we've got a car turning a tight corner at a constant speed. A top view of the motion is shown. The velocity vector for the car points to the east. What is the direction of the acceleration? Well, essentially, you've got something that looks like this with a car that's moving east. Now, again, anything that is moving through any segment of a circular path is considered circular motion, even if it's just rounding a curve. Now, if you kind of mentally fill in the rest of the circle, right, your centripetal acceleration always points towards the middle of that circle. So in this case, if we're looking at this being a compass rose, where this is northeast, southwest, if its velocity is eastward, then its centripetal acceleration is southward. But again, the key is recognizing that even if it's just moving in a segment of a circle, you're dealing with circular motion. All right, so just like in simple harmonic motion, right, we're still going to be dealing with the ideas of period and frequency. And the definition for those two hasn't changed at all. Right, period is still the amount of time it takes for an object to complete one cycle. In the case of circular motion, that cycle is one full revolution. Right, so if we're looking at period, right, period we can consider as seconds per revolution. Whereas your frequency, right, would be revolutions per second. So the period is going to be how long in time it takes to make one full circular path, whereas the frequency is going to be how many times it makes that full circular path per second. And again, same thing still applies. Your period is 1 over your frequency, and your frequency is 1 over your period. Right, so they're still inversely related. Your frequency is still going to be measured in hertz for now. Eventually we'll get to another unit, but for now it's still in hertz, and your period is still going to be in seconds. Now, if we want to come up with an equation for the speed of something moving in a circular path, well, we can go back to the first equation we ever learned. Right, and that first equation for anything moving at a constant velocity was that your velocity is equal to position over time, right? A change or a displacement over time. Now, in this case, if we're dealing with something moving in a circle, well, let's just say that the displacement we're looking at is 2 pi r, right, which would be the full circumference of a circle. Well, how long of a time period does it take to complete one complete revolution? Well, we call that the period, right? So your velocity in this case we can discover as the circumference over the period. Or if we want to alter that just a bit, remember that frequency is 1 over period, so we can also find it by looking at 2 pi r times your frequency. Right, and this should start looking familiar to you based off of what we covered in circular motion. You saw this show up a lot. So let's take a look at example 6.2. In 6.2, we've got an audio CD, has a diameter of 120 millimeters, and speeds up to 540 RPM. RPM just means revolutions per minute. When a CD is spinning at its maximum rate, how much time is required for one revolution? So the period. And if a speck of dust rides on the outside edge of the disk, how fast is it moving? What is the acceleration? So let's just start by pulling out what we know. Now, the radius in this case would be half of the diameter of 120 millimeters, which is 0.06 meters. We know that it speeds up to 540 revolutions per minute, so keep in mind that is giving us a frequency just in the wrong units. So our frequency is 540 revolutions per minute. And so we can always convert that into revolutions per second, which is hertz, which would give us 9 hertz. So if we want to know how much time it takes for one revolution, well, the period is 1 over frequency, right, which is 1 over 9. So our period in this case is 0.11 seconds. So the second thing they ask us is, if a speck of dust rides on the outside of the edge of the disk, how fast is it moving? Well, our speed is determined by a distance, the circumference, over your period, right, which would be 2 pi times our radius of 0.06 meters over a period of 0.11 seconds. So that velocity comes out to roughly 3.4 meters per second. Right, so that's the instantaneous velocity of that speck of dust riding at that distance from the center of the rotational motion. Now, obviously, the greater the radius that dust is going to be located at, the greater the speed it's going to have, the greater the instantaneous speed it's going to have. All right, and lastly, we want to know the acceleration. Well, centripetal acceleration is your speed squared over r, which in this case would be 3.4 meters per second squared over 0.06 meters, right, which gives us an acceleration of 191.9 meters per second squared. Alright, so let's take a look at Stop to Think 6.1. We've got 4 different circular paths, and we want to rank in order from largest to smallest the period of motion of particles A through D. So pause the video, take a second, and see if you can't figure that out. Alright, so we know that speed is equal to 2 pi r over your period. So let's go ahead and rearrange that to where we get period is equal to 2 pi r over v. Now if we look at it, the period is really going to be dependent on that radius to velocity ratio. Right, so if we look at A is v over r. B, A is R over V. B is R over 2V. C would be 2R over V. And D would be 2R over 2V, right, which is equal to R over V. So if we're ranking the periods from largest to smallest, well, C would be number 1. Then you'd have a tie between A and D, and then you'd have B. So again, because they share that 2 pi, right, the only thing we're interested in is this ratio between the radius and the instantaneous speed. So now let's look at what's happening when we're talking about dynamics, when we're talking about circular motion. So the forces involved. Now keep in mind, right, Newton's second law says that the net force is equal to mass times acceleration. Well, when you have circular motion, we know that that's a very specific acceleration. It's the acceleration, the centripetal acceleration. Well, centripetal acceleration is v squared over r. So your net force is equal to mass times the instantaneous speed squared over the radius of the circular path. Now, this net force, we're going to give a very specific name to, right? And that's going to be the centripetal force. Now again, think back to what we said centripetal meant in Latin. Centripetal means center seeking. So if you're looking at something moving in a circular path, the centripetal force is always a force that's directed towards the center of a circle. Now, here's the biggest mistake people make, is they want to think about the centripetal force as some sort of independent force that we've never seen. No, the centripetal force is just a new name for the net force in circular motion. So the centripetal force is going to be a force that is already familiar to you, whether it's friction, tension, or a combination of these things. It's not a brand new force, it's simply the net force when we're dealing with circular motion. Right, so don't fall into that trap of thinking that this centripetal force is some brand new force that we've just discovered. Right, it's just a combo of things we already know. It's just a fancy name for the net force in this case. Right, so the centripetal force points inwards, the centripetal acceleration points inwards, and your instantaneous velocity points tangential to both of those vectors. So let's take a look at conceptual example 6.4, forces on a car, part 1. We got engineers, they design a curve on a road to be segment of circle. They design dips and peaks in roads to be segments of circles with a radius that depends on expected speeds and other factors. A car is moving at a constant speed and goes into a dip in the road. At the very bottom of the dip, is the normal force of the road on the car greater than, less than, or equal to the car's weight? So go ahead, pause this, see if you can't reason that out. Alright, so we're dealing with a dip in the road. Alright, so the car is at the very bottom of that dip. Now, if we complete that circle in our mind, we know that the centripetal force, which I'll just kind of put over here just so I can draw everything else better. The centripetal force is going to be upwards, right? Because it's pointing towards the center of the circle. So your net force is an upward net force. Now let's go ahead and build a free body diagram of this car. Well, the car has weight, and the car also has a normal force. And so we know at the bottom of this dip, the normal force has to be greater than the weight of the car. And the reason we know that is because the net force is directed towards the center of the circle. So if the net force is directed towards the center of the circle, we know that this upward force must be greater than this downward force. So looking at example 6.5, forces on car part 2, we're given that a car is turning a corner at a constant speed following a segment of a circle. What force provides the necessary centripetal acceleration? So go ahead, pause, see if you can't reason this through. Alright, so in this case, let's say this is the road we're looking at, and this is top view, and you've got your car. Well, what force is allowing that car to make that turn, to experience that centripetal acceleration? Because keep in mind, if something experiences an acceleration, there needs to be some net force. Well, in this case, it can't be gravity, it can't be normal force, right? Because those are vertical forces, and we know that the acceleration and the net force, right? So both the net force and the centripetal acceleration are directed towards the center of the circle. So any vertical force won't contribute to the actual acceleration. Well, what do the tires and the road have between them? Well, they've got some amount of frictional force. Right, so the frictional force is the force that provides the necessary centripetal acceleration. Right, and think about it logically, just from everyday experience. You can take a turn a lot faster in dry weather than you can in icy weather, right? And that's because the force of friction is different when the road is icy versus when the road is dry. And so the last thing we want to look at is example 6.6, analyzing the motion of a cart. We got an energetic father. He places his 20 kilogram child on a 5 kilogram cart to which a 2-meter long rope is then attached. He holds the end of the rope, spins the cart and child around in a circle, keeping the rope parallel to the ground. If the tension in the rope is 100 newtons, how much time does it take for the cart to make one rotation? So go ahead and see if you can't set up that problem before continuing. Alright, so basically the scenario is you've got circular motion. We're going to say this is a cart. We know that is attached to a 2-meter rope, right? And that would be your radius. We know that the mass of the kid is 20 kilograms. The mass of the cart is 5 kilograms, right? So the overall mass is 25. We know that there is a force of tension of 100 newtons. And we want to know the time it takes to make one revolution. So we want to know the period. So we got a radius of 2 meters, a tension force of 100, and we've got mass. Now, in this case, there is no other force that's acting horizontally. Again, this is an overhead view of the child being swung around by the father. So there's no other force acting horizontally on this other than tension. So if we look at net force being equal to mv squared over r, well, tension is equal to mv squared over r. And actually, since t is period in this unit, we might want to actually put ft just to be extra clear. So 100 newtons is equal to 25 kilograms times our unknown speed over a radius of 2 meters. So if you solve out for the instantaneous velocity, or the linear speed of the child, you get 2.83 meters per second. So given that, we know that speed is equal to 2 pi r over the period, right? So if we're looking for the period, it'd be 2 pi r over your linear speed. So 2 pi times 2 meters over 2.83 meters per second. And we get a period of 4.44 seconds. Alright, so every 4.44 seconds, that kid makes one complete revolution. Now, we're going to pause here. I'll keep going through the notes in the next lecture. It's a fairly short unit. Just make sure that you have been submitting the practice problems, that contribute to that final formative grade. But yeah, other than that, I will upload another video probably Friday, and yeah, I'll see you then.